yesterday. What's a compact set?
Compact set.
I want a definition, not examples. Bounded and closed.
Okay, okay.
Okay, so it's bounded if it's contained in some large ball centered somewhere, and it's closed. We know that since chapter 2. If you take a set of points, a sequence of points in the set that converges to something, the thing to which it converges is also in the set. Okay. And so, I stated for you yesterday the theorem, which got red marks all around it. Maximum value theorem, which says what?
Suppose as.
I don't want you to dictate, Matthias.
Okay. It just says that like if S is compact, then there's a function.
No.
Wait.
And if there's a function,
And if there's a continuous function, then S
reaches
compact.
then that continuous function must take on its max and min on the set. So if S is compact and F is a continuous real value function on S, then F, I'll write down what I said yesterday, there are points Y and Z in the set. So Y is going to be the minimum point, Z is going to be the maximum point. So the values of the function for all x are between f of y and f of z. Now, our intrepid camera person yesterday asked me a question at the end of class, which some of you should have asked. Anyone want to guess what the intrepid question was?
I remember that our question.
So Cameron's question was, what does it mean on a random set S to have a continuous function? So we've talked about continuity on all of Rn, we've talked about it on an open set, but we actually haven't talked about what it means for a function to be continuous on a random subset of Rn. Tim looks askance. Any thoughts?
Yeah.
So for example, suppose I was just talking about the function on the rational numbers, not to find all real numbers, say, but just think about rational numbers. Suppose I took the following function. Is that a continuous function?
Yes. Root 2 is not irrational.
Root 2 is not a rational number, so this function makes sense on the set of all rational numbers. Is it continuous?
Not in
No, because
No, I don't.
Q is not continuous.
No, this is
I
square
don't
root
like
of
it.
2.
That's not what I'm saying.
Square root of 2 is not a rational number, is what Cal was saying. So recall, square root of 2, this is actually a proof that probably most of you have seen in your lives, that the square root of 2, this goes back to Euclid,
Yeah,
But the square root of 2 is irrational.
Pythagoras pushed someone off of a boat for proving that. Pythagoras pushed someone off of a boat for proving that.
Oh, is
He
that
couldn't
right?
swim.
Wow, I don't think.
And simultaneously, Archimedes yelled Eureka. Oh no, that was in his bathtub, never mind, that's next semester.
What?
Not a total joke. So, what should it mean to say a function's continuous? Go back to what we were talking about earlier this semester. What does it mean to say a function's continuous?
Limit x approaches a.
Okay. So the limit as x approaches a of f of x is f of a, which means that as the points x get closer to a, f of x gets closer to f of a. It's closer and closer and closer.
So would you have to?
Does that mean that like, if you plug in, get closer and closer to plugging in a rational number, you should be able to get an irrational number out?
No. All I'm saying is what you just told me as a definition, I think is a perfectly reasonable thing still to say. Matthias.
Would you have to take, the limit as x approaches a, but you could only take sequences that are in the actual
Yeah.
rational numbers?
Yeah. So you should still say limit of f of x equals f of a as x approaches a. But now in this case you would just say, oh, but x has to stay in the rational numbers. So you don't, f is only defined on the rational numbers, fine. So only take points that are close to a and are still rational. So it's completely intuitive, actually. You take your usual definition, all right, the usual definition is, if you want that f is continuous at a if for every epsilon, pretend you're studying for the final, for every epsilon there's a delta such that whenever
X minus magnitude of x minus
It's less than delta.
and efficient,
And 0.
and we have continuous, right? So it's not the limit definition, it's continuous,
Yeah.
means that whenever this is true, we have
F of x minus f of x. Absolute value.
yeah, I'm doing absolute value instead of magnitude because I'm doing real value here.
Yeah.
Okay, so all I have to do is edit this or footnote it or something and say x belongs to s. So I just say when I'm close to a amongst points of s, then I have to be within distance epsilon for the function f. That's it. Now, Matthias, I think, was thinking about the sequence definition. Remember, we had a sequence characterization. That was one of the proofs I said you should understand by the end of the semester. You could characterize continuity in terms of sequences. F is continuous at A, provided
For every xk sequence.
for all sequences converging to A, f of xk converges to f of A. So for all sequences xk converging to A, we have f of xk converging to f of A. And now how do I edit that?
xk and n.
Yeah, you just have to make sure your sequences all live in S. And so that makes sense of continuity on any sort of weird set in Rn that you want to talk about. Those of you who want to understand what continuity means in totally more abstract settings will eventually take real analysis and topology and learn more stuff there. But this is plenty for us. Okay. That was a side remark. I'm going to do the proof, as I said, today and tomorrow, but I want to go on with the discussion we had at the end of last time. At the end of, that's not a very Should they get Mallory to do it?
You should do the dotted lines.
So recall we defined for any linear map T mapping Rn to Rm, although I stated it in terms of a matrix yesterday, n by n matrix A, we talked about seeing the maximum amount that the matrix or the linear map stretched vectors. So this is going to be something we want to do. This is going to be very important for stuff later in the course, that you want to control on how distances get stretched by functions. And so the first case to talk about is linear functions. We said, define, I didn't quite say this yesterday, so define, this is terrible notation. It's the double bars again. It doesn't mean magnitude of a vector. This is norm of a linear map or norm of a matrix, and it's different from what we've been doing. So if you like, we could put it in separate colors, or we could put 3 bars.
Put it across. 2.5.
So we could add SU notation here, but I'm going to hope that it's clear from context that when we're talking about a matrix here, we're thinking of it in the sense of a linear map and taking norm in this sense. So this is called the norm of T, and what it is the maximum of the magnitude of T of x for all unit vectors x. So you take all unit vectors, you see where they get mapped. So you take the unit circle, for example, and you see where your linear map maps all the points in that unit circle, and you say to yourself, what's the longest vector in this set? There's 2 of them. But this length, if this length here is 1, and this length here is square root of 5, then
The other length is also square.
this other length is also square root of 5. But then this length here is going to be what we call the norm. Well, I'm not saying there's a unique x. In fact, there isn't a unique x where the max occurs. But there is, by the maximum value theorem, we argued this yesterday. Matthias, I'll get to you in a sec. We said yesterday that there is a maximum because we're looking at the unit sphere, which is compact, and we're taking the function. So S here is going to be the unit sphere, and we're mapping S to R by taking the magnitude of T of x. And you guys told me yesterday why this is a continuous function. You said you've proved in homework that linear maps are continuous, and you're composing with the function magnitude of vector, which you've also proved is continuous. So this is continuous by composition of continuous maps is continuous. S is compact. Yes, sir?
So, did we say that the gradient was the norm of the derivative? Because I thought I saw that on the book sometime, but...
No. The gradient is just the derivative turned on its side, thought of as a vector.
Oh, okay. But is there like a relationship between that?
But the directional derivatives are normally taken with some dimensions, magnitude of something one.
So the magnitude, the length of the gradient vector is the largest possible directional derivative. So you're saying this is analogous.
Right.
You're saying apply, okay, very cool. You're saying consider directional derivatives of f at a point A in various directions v. Right? And we said this, for a differentiable function, this is the derivative of f applied to the vector v. talked about taking the maximum directional derivative among all unit vectors, right? And we said that's what the magnitude, the length of the gradient was. So we said that the length of the gradient, this was in fact on the last test among other things, right? The length of the gradient we said was the maximum over all unit vectors of the directional derivative. That was by Cauchy-Schwarz that we said that. But what you're now saying is, hey, this looks very familiar. This looks like we're saying, oh, look, take the linear map, df at A, and take the max that you get when you apply it to all unit vectors. Well, that's exactly this. So what you have now observed is that the norm, so here I'm doing the red bars. The norm of the derivative as a linear map is in fact the length of the gradient vector. And that's going to come up actually in the examples we do. So that's cool. Thank you, Matthias. So, you guys asked yesterday, and Dan asked, but he's not here to ask again, whether this was related to taking what you saw in a homework problem where you think of the matrix as an n by n array of numbers and take the sum of the squares of all of those numbers in the square root, which is generalizing something like this. So let's do some examples. Suppose A is a diagonal matrix. So if you wanted a matrix with numbers in it or a matrix with letters in it?
Colors.
Colors.
Both?
Oh, yeah, let's do it.
Letters.
Teal. Shapes. Shapes. Shapes.
Squiggles. Multiple squiggles.
Or names.
Anyone ever tell you guys you're a pain in the butt? So for example, you could have a matrix -4, 1, 0, 3. So those of you who wanted letters or colors can think about this one, and those of you who wanted numbers can think about this one. I'm going to ask you, what is the maximum amount that that linear map stretches vectors?
There's some grid that determine it.
That's a reasonable guess.
Square root 26.
So those of you who are advocating the square root of the sum of the squares are giving me some crazy number like square root of 26. Thank you, Matthew.
26.
Anybody else have a vote?
Yeah, probably.
I'm asking what the norm of this matrix is, namely, if you multiply this by all different unit vectors, what's the longest vector you'll ever get? So far, no one's given me the right answer.
4.
So it's not the square?
4.
Oh.
So 4 is in fact the right answer. So the answer is going to be, I didn't ask the question, but I'll ask it and answer it at the same time. The norm of A is the maximum of the absolute values of the entries on the diagonal. So in fact, it is not going to be the square root of the sum of the squares of the entries in the matrix. It's going to be something much simpler. Is it obvious to you that there is a vector that's stretched by a factor of 4 for this matrix?
Yeah.
One of the standard basis vectors.
Yeah, the first one.
Is it obvious that there's no vector that's stretched anymore? Well, you guys are saying, yeah, I'm not so sure it's so obvious.
What would you call the unit vector for which the stretching is maximum at?
You could call it the maximum point for that function, but we don't normally have a name for it.
Okay.
The point at which the max
So
occurs.
would we, is that used very much, or is it not?
Well, when we start doing applied max-min problems, we'll actually care where that y and z occur, but for this purpose, we don't have a name for it.
Okay.
So, clearly, the norm is less than or, is more at least that max. Because if di is the maximum, if you multiply a times ei, you get di ei. Yeah. And so the magnitude of a ei is the absolute value of di. So since that is one of the values that we get, the maximum is at least that big. Right? The question is, why couldn't there be a vector that's stretched more than that?
Because it has to be.
So why can't there be, or why can there be no vector stretched more than this? Right, I'd have to make up a vector that got stretched more, but how do I know I can't? Done.
Because you took that same vector, right, and you made that initial entry that is multiplied by the 4 less than 1. You made some of the other entries like small numbers, right?
You don't think you'll ever catch the 4?
Yeah, exactly.
Yeah.
You guys believe that?
Yeah.
Yes.
Could we multiply?
Or can we write a proof?
No.
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 No. And shapes.
Is someone declaring the independence here? We're done with independence. All right, say you took a vector x1, x2 up to xn, and you computed ax. What would you get? So if you multiply this matrix by x1 up to xn, you get d1 x1, d2 x2. And as long as you guys are being so silly, you might as well have an R2D2 somewhere.
Oh.
All right. So tell me about the length of said vector. So I'm trying to do what Jonathan was talking about. All right, square both sides in Dan's honor. So what's the magnitude of ax squared? Well, what's the biggest that can be? The max of the d's. Look, if d1, say, for the moment, were the biggest one, I could replace all the other d's by d1, and that would just make everything get bigger, because I have sums of squares here. Right? Let me emphasize this. This is d1 squared, x1 squared, plus d2 squared, x2 squared, dn squared, xn squared. These are all greater than or equal to 0.
Well, they're all 1.
Yeah, if you putting together than the magnitude of x.
Well, no, I don't want to do that yet, but I want to say these are all greater than or equal to 0, so if I make the d's bigger, the sum goes up or stays the same. So this is less than or equal to the max of the di squareds times
the magnitude of
x1
x,
squared plus up to xn squared.
which is the magnitude of x.
You all agree with this? If you bump up all the d's to make them all the biggest one, you made the sum stay the same or get bigger. Well, but this is telling you that if you take square roots now, what's the biggest the square root of this can be? It's going to be the max of all the absolute values times the magnitude of x.
And we have a greater than or equal and less than or equal.
We do. So if you now say, consider magnitude x equal to 1, you see that the biggest magnitude ax can be is the max of the di's, absolute values. And we already said it was at least that big. So we're done. So putting star together with star star, we're done. So this is the red norm bar. Well, would that all matrices were diagonal matrices. I've seen a few that aren't. So what do we do with those? Row reducing. But row reducing is going to mess up norm. When you do row operations, no one's going to say that you're not changing the norm.
But if we know how we're changing it.
But do you?
Good question.
So there is one of the challenge problems that's coming on the next set, which asks you to think about the norm of a product of two matrices.
So,
Not that very many of you are doing challenge problems, but maybe you'll be impelled to do one.
but I just, yeah, 'cause that would become useful because the.
Yeah, that might be useful.
The E thing.
That might be useful. Of course, this was only for square matrices. We didn't talk about what to do with a non-square. I don't know what a diagonal matrix means if it's not square.
Can it be?
You have either too many rows or too many columns. But I want to come back to Matthias's question. Suppose you take a 1 by n matrix. So let's say it's the transpose of a vector, right? That's what a 1 by n matrix is. What is the norm? Oh, need to keep the red chalk with me. What is the red norm of this matrix?
Magnitude of A.
Magnitude of
The
little a?
Yeah. Yeah, that makes sense.
What's the proof?
You can like
take
A times
Multiple.
So I'm supposed to take a times x for all unit vectors x.
Right,
So that's A transpose times that, which
is A
this
dot
is
x,
A dot x.
Ah,
which is less than or equal to.
look familiar, doesn't it?
Yeah. Hershey.
So when do you get the biggest a dot x for all unit vectors
And the
x?
magnitude is A.
What?
Yeah.
Can't be.
When-
Unit vector x.
When they-
Unit vector of A.
Oh, when x is equal to, well, is a unit
It's
vector.
in the direction.
Right. So you take a unit vector in the direction of a, which is really the same argument we used back when we did the anteater stuff. Okay, and what do you get when you put in a over magnitude a and you dot with a?
A dot A.
A squared.
You get magnitude a. Okay, well since you guys are so smart, I'm going to give you souped up version of that. Souped. You like that, Nick? So, here's one for you guys to think about. Don't only yell out the answer at once. Actually do think.
42 low.
What is red norm of 2, -1, 3, 6, -3, 9?
Okay.
I'll take nominations of answers after you've thought for a little bit. You have an answer?
Yeah, if I can do that. Let me see.
Is this related to something we've talked about somehow?
I think it's related to the.
Mallory's voting it's related to her suggestion. That's a little egotistical, but I'll allow that. What is special about that matrix?
The second row is 3 times the
It is
first row.
ranked as
It's
one.
got rank 1. The second row is a multiple of the first row.
Okay.
Does that give you a hint?
Yes.
Yeah, so it's a unit vector in the direction of the first one.
And so what's the answer going to be?
Magnitude of the
It's gonna
Could be
be
2, 6, or
3 times,
2, 6.
3 times the magnitude of like the,
Over the magnitude.
Is it, well, no, that'd just be 1, never mind.
So you guys have observed that A is the vector 2, -1, 3 times the vector 1, 3. Now, we haven't written stuff like this before. Does this make sense to you? I'm not putting this over there, in which case it wouldn't make sense. Do you see that this gives you a 2 by 3 matrix that is my matrix A?
Yes.
is it forward, 14
So now, can you tell me what the norm should be thinking about this?
Well,
Magnitude of the first row vector? Does it take the first row, transpose it into a vector, and take the magnitude of that vector?
Or you're ignoring this.
That's the largest plus the or.
So you're telling me that if you think about multiplying A by X, that should be analogous to what we did a minute ago
Yeah.
if I regroup. So you're telling me that to make this biggest, I should take X to be a unit vector in the direction of that.
Yeah.
so that's gonna be 2 over.
So we should get
15.
the largest value of this when X is the unit vector in the direction of 2, -1, 3, and so that would be 1 over something.
Root 14.
And what would the largest value be
Um,
by
1 over the
Root 14.
just root 14? So it's the exact same thing if I ignore the 1, 3 as what we did a second ago. But you don't get to ignore 1, 3. You got to use the 1, 3.
So it's root 140. It's the square root of 140, right?
3 squared 14.
14 plus
What? No.
You got it.
What?
yeah.
Look, whatever X you put in, you get a number here. You're claiming that the largest that number can be is square root of 14. What's the length of AX in terms of that number?
What?
So if I take the absolute value of this quantity, my erasing's made it hard to read here. If I take the absolute value of this quantity times the length of the vector 1, 3, that's the magnitude of AX. What's the magnitude of 1, 3?
Square root 10.
And what did you tell me about this quantity?
Square root 14.
It's at most and in fact, does it equal this for some x?
Yes.
Namely, that x. So what's the maximum?
2 root 3.
Square root of 140.
So what's the norm of this matrix?
Or root 140.
Calculators. Agreed? Okay. So, what kinds of matrices do we know how to find the norm of?
Rank
Rank 1.
Diagonal and rank 1.
and 1 by n.
But that's rank 1.
Well, that's rank 1.
Good point.
If I just write down a random 2 by 2 matrix, you realize it ain't so obvious. But it sounds like it's a max-min problem that you have to solve. Oh. Guess you'll know how to do it in a few weeks.
Wow.
Not me, not me. Probably
So I want to make, just because this will come up possibly later this semester and for sure next semester, I want to make a couple of comments about this norm. So a couple of comments on this norm of linear maps. So one that's actually useful, and I've sort of hinted at it in what we've said, is we defined the norm, it's erased, in terms of maximizing among unit vectors. If you take any vector x, not necessarily a unit vector, okay, so let's see. So Nick is telling me to divide by its magnitude. Well, I can't just, so assume x isn't 0. Then how could you write x in terms of a unit vector in the direction of x? So here you are with an x, and here's its unit vector. How are they related?
You could do the magnitude of x. It's like the unit vector times the magnitude of x.
So I scale the unit vector. Right? If I scale the unit vector by the magnitude, then of course the magnitudes cancel and I just have x. Now how can I rearrange using the fact that I have a matrix A or a linear map going on here? What is a linear map of a quantity like this?
Linear map of like taking out the
So I can pull out
scalar first.
magnitude of x. And then I'm left with magnitude of A times unit vector. But what do I know about this quantity?
That's
So it's
the
the
norm.
matrix norm, right? The red norm. So this is less than or equal to the red norm of A times the magnitude of x. So we said it was the maximum amount it stretched unit vectors, but in fact it now follows that it tells you it's the maximum amount it stretches all vectors. That's because of linearity. So if you, okay? So that's useful because if you have a linear map and you want to know the biggest magnitude AX can be, you just have this formula. If you knew the norm of the matrix, the red norm, then you know what, you have an inequality. Okay, another comment. If you take two m by n matrices, or two linear maps from Rn to Rm, what can I do with those? What algebra can I do to two m by n matrices?
Multiply.
I can't multiply.
Add.
Okay,
yeah.
don't be so difficult.
Add.
Add. What do you think red norm
The norm type.
of A plus B should be?
Norm of A plus
So think about it a bit geometrically. This is where I'm asking you what's the maximum amount A plus B can stretch vectors.
norm of A plus the norm of B.
Okay, so I'm going to write down,
Is less than or equal to, yeah. Oh, because it's triangle.
Yeah, triangle.
this is looking triangle inequality-ish, isn't it?
Because if you,
Yes, it is.
Yeah.
So do you believe equals, all you people that were telling me equal?
No.
Only if they.
we no longer commit to that heresy.
I mean, even in the case of a 1 by n, you wouldn't have equals unless they were scalar multiples of each other. The other reason you shouldn't believe equals is that this quantity is attained for some unit vector. This quantity is obtained or attained for some unit vector. They're not likely going to be the same unit vector. So you would have equality here precisely when the max is attained for the same x, which isn't very often. But can you convince me that less than or equal is correct?
Wait, would the max would be obtained for the same x when they are scalar multiples, but is that an if and only if statement?
Pretty well. Well, I'm not sure quite how to answer your question. Are you referring to the A and the B, or are you referring to X?
A and X. I think I'm not sure. I'm not sure how to ask my question.
You're saying you're asking if it's the same unit?
So
it's
this is the max of AX for unit vectors X. This is the max of BY for unit vectors BY.
So only when x equals y.
And we're asking, when will you have the same X that works for both of those?
yeah. When will y equal?
So are you asking, will that happen only if the matrices are scalar multiples of each other?
Yes.
No, it can happen more generally than that. Think about this example.
Yeah, you can switch to.
You could have two matrices with both the same vector here, but different scalar combinations here. So that your two matrices would not be scalar multiples of each other, but you would still have the same x working.
Okay. But is there something we could always say about them, or say about them when they are in specific form?
Well, so in that case, if the matrices have rank 1, if they're both multiples with the same, so if they're both vectors times the same row vector, then it will work. But for more general rank, too hard. Statistically, probabilistically, not going to happen, but I'm not prepared to answer your
Is
question.
there something we call those two matrices?
Something with who?
Would we call them something? Right to one another, or?
A and B.
Keep your question in mind as you start to work problems where you compute these things and see if you can get somewhere. But I don't think it's going to I don't think it's going to happen very often. So what's the proof of this? Well, let's look at a plus b times x and take the length of that vector. This is the length of the vector ax plus the length of the vector bx. And now you guys already saw this. Whoops.
Wait, what?
Typo. It's the length of the vector ax, I was ahead of myself, plus bx. And now you guys already said triangle equality. That's where I was, sorry about that. Okay, well, what did we just prove? We just proved for any x, the magnitude of ax is less than or equal to the red norm of a times x, and the magnitude of bx is less than or equal to the red norm of b times the magnitude of x. So this is, it's getting annoying. Red norm a plus red norm b magnitude x. So what does that mean? Well, it means that if I take the maximum of this over unit vectors, the biggest it can be is this number times 1, which is what we had. But following along what Matthew was saying, in order to have equality hold here, you would need to know that these two vectors were scalar multiples of each other. Positive scalar multiples of each other. So you would need to know that you actually had the maximum ax and the maximum bx for the same x. And they would have to be, ax and bx would have to be positive scalar multiples of one another. So the question is, when does that happen? Other than what I said, I actually don't know the answers. And the last comment is composition. If A is n by n and B is n by p, then you can ask about, what do you know about the red norm of the product matrix? So that came up earlier. And the answer, this is one of your challenge problems. It's not very hard, actually. So I'm giving you an easy challenge problem to do. The answer is it's less than or equal to the product of the red norms. Again, very rarely equal. But the composition of two linear maps can stretch vectors is the product of how much each one can stretch individually. That makes intuitive sense. But again, it would usually be less than or equal. Okay, so tomorrow we will actually prove the maximum value theorem. And along the way, we will need a very useful proposition, so we'll work on both of those tomorrow. Next homework will be compactness homework plus starting max min stuff, which will start on Friday.